Today we're diving into Qwen2.5-Omni, a multimodal model that can process text, images, audio, and video, and respond in both text and speech in real time. The key idea? A two-part design called Thinker-Talker, where the thinker handles understanding and text generation, while the talker turns that into spoken language. To align audio and video inputs, they introduce a new positional embedding method called TM-Rope, which helps the model keep track of time across different signals. We'll walk through how it handles streaming inputs, keeps latency low, and balances multiple tasks without the outputs getting in each other's way. Let's take a closer look.
Let's dive in and set the stage for what this new model, Qwen2.5-Omni, can actually do. Ever wanted a single end-to-end model that understands text, images, audio, and video, and responds in real time with either spoken language or written text? That's exactly what's happening here. It doesn't just switch between modes, it fuses them. How does it handle all that input? Instead of dumping everything into one huge model, it splits the job. Visual and audio encoders break things into manageable blocks, and a large language model called the Thinker handles the long-range reasoning. To keep audio and video synchronized, the paper introduces a new technique called Time-Aligned Multimodal Rotary Position Embedding, TM-Rope. This clever approach tracks where everything occurs in time, so audio and video align like perfect subtitles. For generating both speech and text, they use a Thinker-Talker architecture. Thinker tackles text generation, while Talker converts those ideas into spoken language. They're not separate systems, though. They train together, and Talker even listens to Thinker's internal process. To make speech generation real-time, they use a decoder with a sliding window, which helps keep response latency low. Exactly what's needed for voice assistants. Look at the illustration here. You'll see the model solving a math problem from an image, chatting based on audio, responding to video prompts, and giving text-based advice. Imagine ChatGPT, Whisper, and a Vision Transformer, ViT, all rolled into one, but streaming and unified. You might wonder, why combine everything, audio, images, video, into a single system? Well, think about how humans perceive the world. We naturally hear and see things at the same time, then coordinate all that information to respond. That's the big idea motivating this work. The authors lay out several challenges. First, aligning timelines is tricky. If your audio and video get out of sync, it's as annoying as watching a movie with mismatched subtitles. Second, generating different types of outputs, speech versus text, needs to stay consistent. And of course, you need real-time speed. No one likes long delays. Their solution? 3 main ideas. First is TM-Rope, which keeps everything synchronized over time. Next is the Thinker-Talker design. Thinker handles text, Talker handles speech. Kind of like how we use different parts of our own bodies to communicate. Finally, blockwise processing with a sliding window DIT helps reduce latency. They tested Qwen2.5-Omni on benchmarks like OmniBench and AV Odyssey, and it outperformed specialized models built just for audio or just for vision language tasks. That's the takeaway. A single, unified model using TM-Rope for alignment and Thinker-Talker for speech and text outputs. But how does this system actually work under the hood? They split the brain of the model into 2 parts, the Thinker and the Talker. The Thinker is a classic transformer decoder, similar to what you find in a typical large language model. It receives input from audio and vision encoders, those pieces that pre-process raw sound and images. Then it starts generating text tokens based on the combined signals. Here's the cool part. The Talker. Instead of producing text, it transforms those same internal representations into speech. It's set up as a dual-track decoder specifically designed for streaming audio tokens. Those tokens go to a codec decoder that reconstructs the final waveform. Look at the diagram here. It shows how inputs flow into vision and audio encoders. The Thinker processes them and generates text tokens. Simultaneously, the Talker takes that information and converts it into audio tokens. Those tokens move into the streaming codec decoder, which produces audible speech. This architecture keeps text and speech generation in sync. Because the Talker has full access to what the Thinker is doing, it can speak with context, knowing everything said before, who's speaking, and what the conversation is about. Next, you'll see how inputs are processed, how TM-rope keeps them aligned in time, and how the system delivers streaming outputs. Now let's explore how Qwen2.5-Omni perceives text, audio, image, and video, and how TM-rope aligns them. Text goes through standard byte-level tokenization, much like other large language models. Audio is resampled, then turned into MEL spectrograms, using a sliding window of about 25 milliseconds with a 10 millisecond hop. Essentially, each audio frame covers roughly 40 milliseconds of the original signal. They rely on pre-trained encoders from Qwen2.5-VL for vision and Qwen2 audio for sound. For video, they sample frames at a rate that matches the audio's time steps, trying to keep as much visual information as possible while staying in sync. Here comes the time alignment magic, TM-rope. Each input image frame, audio segment, text token gets a position ID that encodes time, height, and width. Text only needs the time axis, but images and audio frames also need height and width. If you have an image, each patch gets its own height and width ID, while the time ID is the same across that entire patch. For video, they chunk it into 2-second segments. Each chunk's visuals and the corresponding audio are interleaved. Video tokens come first, then audio tokens, all for that same 2-second window. Check out how TM-rope makes the model see and hear things in sync. It ensures no signal goes out of place. This helps with stable training and prevents any single modality, like audio or image, from overwhelming the others. Now let's talk about real-time speech generation. Nobody wants lag when talking to a model, right? So how does Qwen2.5-Omni deal with streaming audio outputs? First, the talker receives rich signals from the thinker. These signals encode not just the words, but context, tone, and more. The talker then passes them to a codec model, Qwen2.5 tokenizer, that breaks speech into discrete tokens. Later, those tokens become actual waveforms. Unlike some systems, there's no strict word-by-word alignment. It's learned end-to-end. But what about latency? They define 4 places where delay can creep in, from receiving the input to the final audio output. To cut that delay, they do 2 things. One is support prefilling. Instead of waiting until the entire audio input is ready, the model processes 2-second chunks at a time. Encoders operate in blocks, so they only look at a chunk instead of the full signal. For images, small patches are merged for a more compact view. The other is streaming codec generation. Look at figure 4. You'll see how the model uses a DIT with a sliding attention window. 2 blocks behind, current block, 1 ahead. This restricts how far each token can look back, keeping things computationally light. After generating MEL spectrogram chunks with flow matching, they convert them into waveforms using big VGAN. The result is block-based streaming audio that flows smoothly, with minimal weighting. So how do they train this model to do it all? There's a pre-training phase and a post-training phase. In pre-training, there are 3 stages. Stage 1 freezes the large language model and focuses on training the vision and audio encoders with loads of audio text and image text data. Stage 2 unfreezes everything for end-to-end training on a broader, multimodal dataset. Stage 3 extends the model to handle long sequences up to 32,000 tokens. They use a massive dataset, 800 billion tokens for image/video text, 300 billion for audio, and 100 billion for video with audio. That's a ton of data, but it allows the model to connect textual, visual, and auditory clues seamlessly. Then comes post-training. They use a format called ChatML to fine-tune the model for better instruction following. ChatML is a structured conversation format, marking different inputs like images or video with special tags. Check out the examples here, showing how the model processes a video clip and outputs detailed responses, either transcribing dialogue or describing the scene. Why ChatML? It aligns the conversation flow with how the model understands mixed modal data, letting it respond in a natural back-and-forth style. But how do you train the talker to produce smooth, stable speech under real-world conditions? This section breaks it down. They follow a 3-step recipe. First, talker learns conversational continuation using next token prediction, just like standard language modeling. Second, they apply something called direct preference optimization, DPO, to stabilize the generated speech. Third, they do multi-speaker fine-tuning, so the model can adapt to different voice qualities and become more expressive. They also use in-context learning. That means talker doesn't just get raw text. It sees rich, multimodal dialogue. It learns to map semantic content into speech, with nuances like prosody and even emotional tone. To avoid mixing certain voices with specific text patterns, they add a technique to separate speaker identity from textual content. There's a DPO loss formula here that spells out how the model chooses a preferred speech output over a less desirable one, based on likelihood under both the model and a reference baseline. They also mention reinforcement learning to handle noisy data, using word error rate and punctuation accuracy to filter out badly matched training pairs. Finally, they fine-tune on high-quality speech datasets. The result is a model that can speak naturally, handle different accents, and even show a bit of emotion. Now we get to how Qwen2.5-Omni performs on various tasks. First up, text-to-text settings. They compare Qwen2.5-Omni 7B with other language models, like LMA or Qwen2.5-7B, across benchmarks for general knowledge, math, science, and even coding. Even though Qwen2.5-Omni can also handle audio and video, it still does well with pure text tasks. It might not always top the leaderboards, but it's not far behind. On math-heavy benchmarks like GSM-8K and MAth, it's only a few points shy of Qwen2.5 to 7B. On coding tasks like Human Evil, it's also competitive. Then comes audio-to-text tasks. This includes everything from basic speech recognition to reasoning over spoken conversations. Qwen2.5-Omni does great here, outperforming specialized speech models like Whisper and Qwen2 Audio on many tests. Check out the results on VoiceBench, an average score over 74 for a model that isn't purely audio-focused. Impressive, right? They tested it with and without text-based instructions, but instructions are speech prompts. Qwen2.5-Omni really shines, showing its strength in real conversational scenarios with spoken queries. Look at the audio-to-text benchmarks here. They pack in a lot of data on how Qwen2.5-Omni compares to top models. For automatic speech recognition, especially on the popular LibreSpeech dataset, Qwen2.5-Omni nails a word error rate of around 1.6 to 3.5%, right alongside dedicated models like Whisper Large or Minmo. On multilingual sets like Common Voice 15, covering English, Chinese, Cantonese, French, it hits around 7.5% WER, matching Qwen2 Audio. FLIRS is another multilingual test, and Qwen2.5-Omni pulls in scores above 5 for both English and Chinese. Even on harder audio, like Wenet Speech and Vox Populi, it stays competitive, proving it's not just for clean lab data. And for speech-to-text translation, like turning Chinese into English. Qwen2.5-Omni stands out on VOST2, with top BLEU scores over 40 in some cases. That's quite strong for a model juggling so many modalities. Curious how the model manages emotions, music, and natural conversation? This part reveals more about its audio prowess. On speech emotion recognition, Qwen2.5-Omni outperforms other models by catching subtle vocal cues. For classifying vocal sounds, like claps or footsteps, it's tied with the best. Then we see it handle music in music caps, describing genres, moods, or tempo, with top scores, including a 0.88 on Giant Step's tempo classification. For audio reasoning, check out the MMAU benchmark. Qwen2.5-Omni takes the lead in interpreting sound, music, and speech in context. Voice chatting is next. Look at VoiceBench. Qwen2.5-Omni tops the charts in both simpler tasks and more advanced dialogues, beating out other audio and multimodal models. It can hold real conversations using just audio inputs. Finally, Table 4 here shows how the model responds to spoken prompts, bridging the gap between specialized audio models and text-based LLMs. Even in math-heavy tasks, it keeps up without stumbling. Now let's see how it handles images. Image-to-text tasks, OCR, and even object localization are all in play. Check out Table 5. Qwen2.5-Omni is right up there with models like GPT-4o-Mini and Qwen2.5-VL-7B. Whether it's reading college-level math problems or performing general vision language tasks. On MMBench and CRPE, it scores above 80 and 76, respectively, showing it's more than capable of parsing images into meaningful text. In OCR tasks, like DOCVQA, ChartQA, TextVQA, it achieves near-perfect accuracy, with a 95.2 on DOCVQA. That means it doesn't just recognize random pictures. It handles structured documents really well too. Table 6 dives into grounding, identifying where an object is in an image based on text. Qwen2.5-Omni isn't just competent, it's often in the lead on benchmarks like RefCoCog, RefCoCo Plus Test, or ODINW. It keeps pace or even outperforms. So it's not only describing what it sees but also pinpointing exactly where it appears. What about video and speech generation? The model has to understand sequences of images and transform text into natural audio. Look at Table 7 to see its video-to-text results. Qwen2.5-Omni competes with or beats specialized models like Qwen2.5-VL-7B and GPT-4o-Mini on tasks like video-MME and MV Bench. That means it's capturing context over time, not just in single frames. Table 8 shows performance across sound, music, and speech tasks. Qwen2.5-Omni 7B leads on the OmniBench benchmark, with the highest overall average. This underlines its capacity to unify inputs from multiple modalities and deliver coherent text outputs. They also test the model's speech generation. After all, it's not enough to just process video or audio, it has to speak too. In zero-shot generation tests, it aligns well between the text input and spoken output. No special speaker data needed. Reinforcement learning helps avoid mistakes like weird pronunciation or long pauses. Then they try single speaker fine-tuning. And Qwen2.5-Omni gets even better. It learns the speaker's tone and rhythm, while still preserving its overall language understanding. Finally, we see the results of Qwen2.5-Omni's speech generation in both zero-shot and fine-tuned scenarios. Check out Table 9. It evaluates how well the model's spoken output matches the intended content and whether it captures the speaker's voice. With reinforcement learning fine-tuning, error rates drop, and similarity scores match models like Cozy Voice or SeedTTS. Table 10 looks at adapting to specific speakers. When the model is fine-tuned on someone's recorded samples, it really nails their unique style, tone, pacing, everything, while staying clear and fluent. Its naturalness scores rival human recordings, around the mid-4 range on a 5-point scale. This wraps up the model's speech capabilities. Through in-context learning and reinforcement optimization, it avoids the usual pitfalls like garbled pronunciation or robotic pacing. It ends up being an all-around speech powerhouse, especially when you consider it also handles text, images, and video inputs. Thanks for joining us today. Happy exploring!